Okay, so welcome to this video on storing audio or sound files. So where are we in our story? We certainly know, and we're getting towards the end of seeing how this is true. We certainly know that everything, absolutely everything, is stored in binary. So no matter what format or what medium data is stored in, it's always binary in any device. So what have we done so far? So we've certainly spent quite a bit of time getting comfortable with the idea of binary numbers. We made the natural jump to how about any other types of text or codes, basically keyboard characters. And then in the last video, we explored how might images or pictures be stored in binary, just stored in general, digitized in general, which was a little bit of a stretch, I think, to go from just saying keystrokes on a keyboard, which are sort of very one-dimensional, to talking about pictures, which is very much two-dimensional. So there was a lot that sort of went into that, and the good news is that the topic for this video, which is storing sound and image and music, has a similar sort of strategy, I guess. And so we'll draw some parallels certainly between the last video, or things we did in the last video, and what we'll do in this one for sound and music. And then what else is left is we'll spend some time talking about how instructions, which maybe that isn't totally clear what that means yet, sort of more of the infrastructure of how computers are powered, which is also binary, not so much memory. So the first four topics have been pretty much just talking about how are these items stored as data. Instructions will be more of sort of an action thing, and we'll do that. In the next few videos. But anyway, but for today, sounds and music. How can we store sound? You're listening to me right now, so obviously somehow, somewhat magically maybe, my voice is being recorded, and as you all are listening to it through earphones or through speakers, you're hearing it. So how are we going to get to sound? Well, like I said, there's some similarities between trying to get to sound and what we did last time, which is images or pictures, in the sense that you really have to kind of try to break down sound into components, and also decide, how precisely or with what level of precision do you want to try to record it or play it back, as the case may be. So we'll have similar options, I guess, that you can take a crappy picture or a really nice looking picture, and similarly for sound, you could make a really tough, a really rough recording, or one that sounds much better. So we'll have similar issues like that, and our goal in computers, or in trying to understand computers, is to say, well, the goal was to try to simulate what your eyes do when we were talking about images and pictures. So for sound, we're going to try to figure out how do we simulate with technology what are the sounds that our mouths make when we're speaking, and also the sound that our ears might be able to hear when we're listening. So this is just sort of a good overview of what we're going to try to hopefully explain in this video. So first, just to talk a little bit about different ways or different types of digital formats for music. You all know probably that there's many different file types that correspond to media files in general, and of course probably new ones being added all the time. But generally, you might think about a couple of basic distinctions. The sort of most simple way, and of course this was how representation of sound or of music started, was with what is usually referred to as a MIDI file, which I guess stands for Musical Instrument Digital Interface. And this was sort of a primitive way of trying to digitally represent sheet music or just music in general. And it was done in a somewhat primitive way. It wasn't as concerned with trying to necessarily capture a lot of richness of sound, but was designed to try to hopefully get the tempo, right, the time between notes, um, trying to get that as accurate as possible. And being able to have at least some distinction between maybe different instruments playing different notes and things like that. So this is a somewhat primitive manner of storing sound or music. And if you had an old cell phone, you know, that sounded sort of like carnival music or something, it didn't really sound, even if it was a famous song that you made as a ringtone, it sort of sounded like a terrible version of it. Everything just sort of sounded pitchy, and that's a MIDI file. Certainly, you can still find these in even today. Any sort of tool or device that you might use that's sort of cheap. So probably not your cell phone. At this point, our cell phones are so advanced that they have they have pretty decent sound quality. But any other sort of device, maybe like an electronic game system, sort of a primitive one that might mostly just be making sounds as like little, pitches and not so much music, is maybe playing MIDI files. So it certainly still exists. Now, what's good about MIDI, just like we might have referenced with photos, is that it's not a lot of data. It's not that hard to store a MIDI file. And you can actually do, if you have music that has more than one instrument, you can actually layer these on top of each other and still sound decent at a very small file size. So obviously, as usually is the story, you can get okay quality for small amounts of data. And sometimes if that's all you need, you just need to be able to, sort of recognize this tone. That's fine. That's probably another good example. Ringtones that you have maybe that are actually stored on your phone, chimes and whatever other sorts of pre-recorded things. Those are MIDI files, in that you, again, don't have that many different notes. It's not trying to sound like a 100-piece orchestra or anything. It's just supposed to be a sound, a tone. Anyway, okay, so in the history of trying to represent music, MIDI came first, and then slowly but surely we evolved into somewhat more modern formats, which might be an MP3 or MP4 file, which represents a much higher quality audio. And of course, as you might guess, this requires much more memory in order to be able to store a music file and have it, sound like the band is in front of you, which is more or less what we've achieved, I think, with modern digital music storage. So MP3, MP4, and I know there's other types of extensions on files representing modern music, but we'll use MP3 or MP4 as sort of our standard for current and rich audio quality. Okay, so that's sort of where we are in the music story. But how do we actually, not even just visualize, but how do we even understand sound? There's really no way for us to try to come up with a way. If I say, all right, I think you all believe me by now that sound, just like everything else in a computer, is stored in binary. So I hope you all believe that, an audio file, a song that you have stored on your phone or elsewhere, is a sequence of zeros and ones, right? Kind of hard to believe that 3-minute song that you listened to in the gym yesterday is just zeros and ones, which always is a little tricky to try to reconcile. How the heck does a bunch of zeros and ones turn into that song that had lots of intricate details and all kinds of stuff? Okay, so just like with pictures, where that's a tough sell. At least with the picture, though, you have a physical thing you're looking at. So maybe when we started talking about how to store images or pictures, I mean, the sort of paint by number analogy is pretty good because that's really all you're doing is you're saying a photo. How do you store a photo? Is that you basically split up your medium into a grid and color in the boxes in the grid, and that's how you store it. So that's maybe not as crazy a leap of faith because at least it was a physical thing that we could touch and we could get our hands uh, on a photo. But sound we can't get our hands on, right? Literally, it's just all around us. So in order to even get any sense of how the heck am I going to store the sound as zeros and ones, I at least maybe first have to try to get a visual of what sound is. And if you know anything about sound, maybe you know that sound travels in waves. So, literally through the air, just like light, right? Light also travels in waves. Sound does as well. And this is not a physics class, so we won't go into too much detail, of course, about how sound travels. But one thing you should know is that there are two main components to trying to describe sound, and those are frequency and amplitude. So frequency describes, as the word suggests, the timing of the notes or the timing of the music. So in the little picture down here, this what you see in red or pink, I guess, is trying to represent sound, right, or maybe music notes or whatever you want to say. So frequency refers to not which note you're hearing, but when do you hear it, right, or when do you play it, or when do you record it. So frequency is maybe what you would think about as being the sort of x-axis, in other words, sort of time. This is the beginning of the song, and this is the end of the song. So the frequency refers to the timing, right, of when each note or each sound is occurring. Amplitude, on the other hand, represents the actual sound, right, or which pitch or which note is being played. And so we might imagine that more so, even though I know there's not one on the picture here, on a sort of y-axis. So I might imagine a graph like this, and if this is sound, I'm saying sound starts here and travels through time this way. And what else happens? Oh, okay, the sound is low, and then it gets higher and higher and higher, and then it starts getting lower and lower and lower, and okay, and so on and so on. Right? So amplitude refers to which note is being played. So that's sort of more is it a low note versus a high note, and which one is it? Right? What is the sound that I'm supposed to be hearing right now? And frequency refers to when do I hear this? Right? The timing. So I'm saying, oh, okay, it's at the beginning versus at the end, or wherever it may be. Now, in theory, our ears can hear infinity times every second. Now, I know we don't think about that because we're just saying, well, I'm just listening. I'm not trying to say, oh, I'm listening for music, and now I'm listening for music again, and now I'm listening again. We just listen all the time, right? That's the sort of the beauty of the ears, right, is that they're sort of always on. So in that sense, we're not so much trying to say, what do I hear right now? What do I hear right now? What do I hear right now? We just hear all the time. So that's what I mean when I say our ears can hear sort of infinity things every second, or every whatever time period you want to talk about. So we sort of have infinity or infinite frequency. And also, again, in theory, we can distinguish between either infinity or certainly many different sounds, right? Different notes or different pitches or different whatevers. And again, just sort of think about that we don't stop and ponder. I mean, unless we're really trying to, name a song or try to identify a note of music. But when you're listening, when you're hearing stuff, you're just saying, well, I'm understanding what it is. You guys are listening to my voice right now, and you're hearing words and making sense of what the words are, of course, hopefully. But you're not so much saying, oh, was that sound, that he just made sound number 87 or sound number 88 or sound number 2,962 in my memory bank. We don't think that way, right? Because in our ears, and obviously in connection with our brains, can sort of have infinity distinguishability of different sounds that we might hear. So in some sense, we sort of have infinite frequency and amplitude, which is wonderful for us as humans. Not so great when we're trying to design computer or technology, because technology is supposed to try to, as best as it can, represent what we can do or what we are capable of. And as you might imagine, infinity is pretty darn hard to represent in some mechanical way. So to digitize sound, which is to say to try to record it, let's see if this sort of picture maybe makes sense. So since sound is happening, we might say continuously. In other words, it's just always, we're not chopping it up in our brains anyway. We're not chopping it up. We're hearing it, and we're hearing all the varieties that you could ever imagine. But to actually record it, maybe we should try to do just that. So first, let's chop up. If we think about the pink, sorry, I'll go back a second, right? So if we think about this pink as sound waves, as a sound wave, which it is. So you can actually, I mean, again, this isn't a physics class, but sound, if someone's say you're standing in front of a speaker or something like that, the sound that's emitted from the speaker is actually traveling in a wave pattern like this, or some wave pattern, into your ear, and then you're hearing it and processing and all that stuff. So it does actually occur in a wave like this. So, so the pink here just sort of represents whatever, you could think about it as music, you could think about it as just audio, someone speaking, or whatever it might be. But okay, the point is that it's happening, it's flowing continuously. So in order for us to understand it, let's try to maybe do this. First, let's chop the x-axis, right, which we maybe are going to keep referring to as frequency. Let's chop that up and try to imagine or try to think about those black lines that just were drawn in. Those are going to be the times to try to record music, right? So now I'm thinking about technology, trying to do what we do with our ears. I'm going to draw some lines in to try to emphasize, well, that pink, that real life sound is way too complicated for me to understand if I'm trying to digitize or record it. So what do I have to do? I say, all right, let me at least get myself on the board here by saying, I'm going to declare or chop this up into a frequency like you see here in black. And what does that mean? It means that within each of these intervals, or you could say maybe on each of the black lines, I guess, a recording is going to happen. And by recording, I mean a binary number is going to be recorded, literally. 0, 1, 0, 0, 1, 1, 1, whatever, is going to be stored. So this sound clip, this pink that we started with, I don't know how long it is, let's say it's 20 seconds of audio. I'm going to split it up, and for the purpose of recording it, I'm going to say to myself, at each of these black lines, or in each of these intervals, I guess, I'm going to make a recording. And by a recording, I mean I'm going to take note of a sound. And each sound is, of course, maybe not surprisingly, going to have a binary code associated with it. I'm going to record that code. Okay? That's the best we can do, right? I know this sounds like, well, this is a terrible idea, because we don't do this. We don't sort of say to ourselves, okay, every second I'm going to record a sound that I hear. If someone's talking to you, can you imagine how distracting that would be to say, I'm only going to record one sound every second? It'd be like you'd get just like little blips of sound, I guess, right? You wouldn't actually be able to get words, because think about how much my voice is changing, even just in a second, in order to not just only capture the tone, the sort of rise and fall of the pitch, the also actual sound that I'm making. All of these things are happening very intricately. But frequency, dividing it up this way is going to be, we have to, right? Because computers aren't magicians, and they're also not humans. So they don't have the ability, a microphone, a recording device doesn't have the ability to record sound as well as our ears can hear sound. So this is one step in trying to at least get there, is to say, I'm going to think about frequency, chopping up the time interval, and saying, I'm going to make this many recordings. Okay, so some terminology. Um, Samples per second, the number of samples per second is usually how frequency is described. Okay, so if I say, I don't know how many black bars are here, but let's say there's, I don't know, 40 black bars here. And let's say maybe let's say that this is 1 second of sound here from start to finish. Then I might be making 40 samples per second, and that would be my frequency. Okay? As if to say, right, in this 1 second, let's say this is 1 second from start to finish, I'm going to make 40 recordings of what I hear. And by I mean a recording device is going to record 40 times in that second. 40 sounds a little more reasonable, maybe, than just saying you're going to do this once per second. But believe it or not, if audio, if I was recording this video right now and making 40 recordings per second, I would sound terrible. You wouldn't even, I would sound more or less like a robot. If you think about a robot, it sort of is that sort of very pitchy, just flat sound that has no emotion in it. And why is that true? Because we convey emotions with small little changes in sound that if I'm only recording even 40 times in a second, I'm still not going to pick up on all of those little intricacies that we as humans hear when we're hearing live audio. But anyway, this is the best I'm going to do. Okay, so frequency. So I have an idea that I'm going to chop it up that way. Now the other thing I have to chop up is what notes am I hearing? So this is where the amplitude portion of the discussion comes in. So first of all, chop up the sort of x-axis and say, all right, you're going to make 40, or however many bars I have, 40 recordings. So that's the timing, that's frequency. And then the other thing, what am I going to record each time? That's a good question, right? Well, I'm going to say, all right, I'm going to divide the y-axis, which is sort of the pitch, or if you want to go back to music class, you could say it's the note, I guess. Although it's more complicated than that, because you're not just trying to say I'm playing, a D or a D sharp. You're trying to say more like, oh, okay, it's maybe yes, so maybe there is some musical part of it, but there's also tone and there's a lot of other things that go into sound. But anyway, amplitude is going to try to describe for us, okay, well, what sound am I hearing? Sound, and these are all going to be binary codes I'm going to assign to all the sounds that I might record or be able to record. And so I'm going to ask, oh, okay, so if at this moment, let's say here in this time interval right here, what sound am I hearing, or what sound should I be recording? Well, whatever one this is, right? Whatever binary code maybe goes with this sound. If I look and say, oh, okay, that sound is coming out at that time, at that moment. So I should record whatever the binary code is for that. Whereas at a different time, at this time, for example, what sound am I playing? Looks like more like this sound, right? So I might record the binary code that goes with whatever that sound is. Okay, so amplitude, right, which is supposed to describe for us how many or what are the different notes or pitches and sounds that we can recognize, I might think about that as being the y-axis and trying to say, okay, I'm going to divide the whole range, right? Again, what is the range of sound or pitches that I might hear on this pink sound wave? Well, there's infinity different pitches. Okay, well, we can't do infinity. So instead, I'm going to split this up. This is probably not a fantastic example, but for the visual, I'm going to split this up into, I don't know, 10 or so, 10 or maybe 12 different notes or different sound codes that I can at least recognize and record. Okay, so amplitude is often given in how many bits per sample. Remember, a sample is a recording of what's happening in that moment. So amplitude is often described either in how many different notes can you recognize, or if you want to talk about the memory, it's how many bits per sample. Okay? So I might come through here and say, all right, I've got some codes, I've got some different sound codes that are going to correspond to each space, I guess you might say, right? So there'll be a code for that sound, a code for that sound, a code for that sound, and so on. Those are going to be binary, as we probably know. That's amplitude. So how am I going to record this pink? You can kind of maybe now see at least a strategy, which is to say, okay, start at the first interval, the first frequency interval here, and say, oh, okay, what note is that? Record the code for that note, and then go to the next one and say, okay, What note is that? Record that code. What note is that? Record that code. And then if I sort of do that for this whole song, I at least get a bunch of codes, and they're in sequence, right? I'd say, there's a first one and a second code and a third and a fourth. So I'm getting the sort of tempo, hopefully. And I would have basically an encoded map, I guess, or an encoded way of describing this sound. So for this particular example, I might say, all right, at the first recording, I think I did this for on the black lines, right? So okay, so at the first black line, if I'm going to record right there, I'm going to say, what note is that? Oh, that note is maybe the code for -10. Okay, and then I go to the next one. I say, all right, I'm going to listen here. Where is this right now? I think I rounded that to 0, code 0. And then I go to the next time interval and say, okay, where am I on this third black line? And maybe I'm up here at more like 20, 30, and so on, 30. Okay, and so on and so on, right? So it's sort of just like making, I don't know, I mean, it's like in algebra class when you just are sort of tracing out a graph and you're trying to say, well, what are the y values of this graph as I sort of move from left to right? Those are the notes that I'm going to try to record. Of course, it's going to be binary instead of base 10, but that's the general idea, and that's accurate. That is actually how you're hearing my voice right now, is that as I'm recording this video, the microphone in my MacBook is doing exactly this. It's saying, oh, okay, what pitch code is he saying right now? Oh, write that down. And by write that down, I mean record it in binary. And then the next one, and then the next one, and the next one. So when I hit finalize this video and post it, that's a bunch of zeros and ones that when you are now listening to it, it's just reading them off and playing the sound that goes with those codes. How do you know it's me recording this video and not, someone else? Well, because technology, of course, has advanced to the point where my voice, which you know by now, it's been several videos, you recognize my voice because someone else saying the exact same words as me, even with the same tone or sort of inflection as me, still has a different sound. So anyway, that's the idea. That's how sound is digitized. That's how sound is recorded. So let's take a little bit of time to talk about the two components a little more in detail, and let me try to give you an example of sort of the role that each of them plays, just like we sort of did with images. So again, frequency describes, as the name suggests, how often do you record the sound that's being played or the sound that's being heard. We usually give this number in samples or recordings per second. This is what in ads for things, maybe for sound systems or things like that, is often given in megahertz. So it has very fancy units that, to be honest, it's not all that important for us to understand the sort of labeling of things. But when you hear that number, when you hear something like that, that's referring to the frequency, which for us just means how precisely or how many times do I listen and record a note per second. Again, we can hear infinity things per second, so we try to get as good. We try to mimic this as much as we can. So what would actually happen if you sort of had bad frequency, or sort of if you only listen and record once every second? Then your recording will consist of however many notes you have or however many sounds you recorded, but each of them will play for 1 second, which, again, try to think about me talking to you right now. In each second, it would just take one quick sample of what it hears, and it would and then if I'm playing it back, it would broadcast just that one sound for a whole second. So any part of any of these words that I'm saying, which I'm pretty sure I'm saying most of these words in under a second, any one of those, it's going to just listen at some point while I'm speaking. It's going to take just that one little note, and it's going to say, that's what he said for a whole second. And then it's going to go to, and then in the next second, it would say, okay, I'm going to grab one note from the next second and play that back for a whole second. So I wouldn't sound like a person talking to you. I would just sound like a series of beeps or a series of just tones each of which would play for a second, and that'd be it. So obviously, you have to record more than once every second for your frequency. But okay, but that's the connection. So obviously, the more frequently you listen, the more and record, the more accurately you're going to capture the dynamics, right, and change in sound. So let's just take a quick example here. So if you record 4 times per second, which is, again, not realistic in terms of storing music or any sort of audio, but so that the numbers aren't totally crazy, we'll sometimes just stick with smallish numbers. I'll tell you later in this video what what is my MacBook right now actually recording in terms of frequency, and and the playback as well. So I'll tell you the real world numbers towards the end of this video. But anyway, all right, so if our frequency is 4 samples per second, meaning I'm going to make 4 recordings of what I'm hearing every second. So obviously sort of at the quarter-second mark, the half-second mark, the three-quarter-second mark, and at the end of the second or something like that. Then how many notes will I record, or how many recordings will I make if my song is 3 minutes? Well, this is hopefully not too crazy to compute here. A 3-minute song is 180 seconds. And if I'm recording 4 times every second, if I multiply by 4, I get 720. So if this is my strategy to record a 3-minute song, I'm going to actually record 720 tones, I guess you might say, or 720 notes, that if I play it back, will last 3 minutes. I mean, it's real time. If I recorded a 3-minute song, I'm going to play back a 3-minute song. However, I'm probably live sounding, or the band or whatever is sounding pretty good, but I promise if all you ever played was 720 notes, each of them for a quarter of a second, again, it's going to sound very robotic and just sort of, like a series of just tones, just, beeps and whatevers. So I should say, I shouldn't glaze over this part. However many samples per second you do, each note then, or each tone in the playback, will last 1 over that. Hopefully that makes sense. That if you record 4 samples per second, then when you play it back, each one of them should last a quarter of a second, right? So however many recordings per second you do, each of them lasts 1 over that number of recordings in terms of playback. Okay, so if you record 1,000,000 samples per second, then when you play it back, each one lasts 1 over 1,000,000th of a second. And that's much closer to what we actually experience in the real world for a recording, which again, sounds crazy, but well, we'll get there. So this might sound a little familiar in the sense that frequency is analogous to resolution that we talked about with photos, right? So a high-resolution photo, meant that we could represent curves, right? The intricate sort of curves that we have in the images. In other words, things didn't look super boxy and pixelated if we had high resolution, because we were able to be in tune with curvy images, or curves in images that we could represent with pixels, and we could represent that with boxes and have it look really, really, really good. But we needed a lot of resolution. We needed a lot of pixels in order to make a picture look good. Similarly, for audio, you need high frequency if you want your recorder to be able to detect changing sounds. So I need to record maybe 1,000 samples every second in order to actually capture me saying a word and not sounding like a robot. So frequency, right, is very much the exact same idea as resolution from our images video. Okay, amplitude, the other side of the story, of course, talks about, again, how many possible notes or pitches or tones will you be able to distinguish between and record. So again, our human ear, in theory, can hear or distinguish between infinity, or at least a very large number, of different notes or different tones. So we're trying to mimic this, okay? Again, we don't have the ability to tell a computer or tell a recording device to be able to recognize infinity different sounds. But we could do a lot. We could try to say, all right, you should be able to distinguish between any sort of reasonable amount of change in pitch or change in tone. Um, so again, I'll tell you what in reality what the amplitude of modern music devices is. But so what might I do is I could just say, all right, well, I'm trying to record these notes in binary, of course. So if I'm just thinking about music notes, A, B, C, and so on, if I was just being sort of that basic about things, I might say, all right, maybe I can get by with 3 bits per recording or 3 bits per note. But if I only had 3 bits, right, and I might start to do some codes, so I might say A is 000, B is 001, and so on. Well, if I have 3 bits, if I only have 3 bits, we know hopefully by now the formula, right? 2 to the number of bits is how many codes you get. So if I have 3 bits, I only have 8 codes, which probably isn't enough, right? I mean, I guess if I just have an instrument that only can play 8 different notes, which is possible, right? I mean, I'm picturing a xylophone that a little kid maybe plays with that maybe only has 8 different notes. So in that sense, you might be able to get by. Although even even an example like that, right? If you sort of hit the xylophone sort of not flush and just sort of ping it a little bit, you do sort of get a different pitch than just whatever note was being played. But anyway, in general, so in general, of course, right, if you have n bits per sample, however many bits you're going to let me use each time, that can mean we can recognize or store 2 to the n different possible notes. Okay? So amplitude is usually given to us in how many bits per sample. And obviously, the higher the amplitude doesn't have anything to do with how often you record something. It has to do with what is the richness or what is the depth of sound that you're able to distinguish between. Okay? So the higher the amplitude, the more the additional or the more different notes you might be able to recognize and record, which of course is going to enhance your ability to capture the range or the richness of sound in the real world. But of course, the better I want to be at doing this, the more memory it's going to cost me. If I need to be able to distinguish between, a million different sounds or a million different tones, I'm going to need n. N's going to need to be pretty big, which means I'm going to need to have a pretty large number of bits every time I take a sample. And as we talked about with the frequency, I might be taking millions of samples to record a song because I want to do a lot of them every second. Okay, so this is obviously going to sort of add up. Amplitude, in case it wasn't clear, is exactly the analog of color depth that we talked about with images and photos, in the sense that color depth, which was also bits per, in that case it was bits per pixel, basically said how many colors are in your palette. How many colors can you use to color this picture in? More colors, richer image. Same thing with amplitude. Higher amplitude, more bits per sample, is going to, of course, lead to a richer palette, you could say, a richer assortment of sounds. And that's going to better represent the real world. Okay, so since we've done all of these analogies, the last one to just remind you of then, so the total amount of memory you might need to store a song or some other audio is, well, how many samples did you take? That's the frequency. And how many bits per sample? That's the amplitude. And if I multiply, I should be able to get the total amount of memory. Now use your smarts here a little bit. Number of samples is not necessarily amplitude. It's not necessarily frequency. Frequency tells you how many samples per second. So obviously you have to multiply by how long is the recording. So, think a little bit about this before you just say, oh, it's these two numbers multiplied together. Well, it is, but number of samples is oftentimes frequency times length of song. And also just make sure you have your units correct. If the frequency is given in terms of seconds, samples per second, which it usually is, and your song is 5 minutes, you have to convert from minutes to seconds before you throw that number into this formula. But yes, it's the same idea that we had with photos, which is that memory is resolution times color depth. Same idea here. Memory is frequency times amplitude, but just use your smarts a little bit when you're doing this computation. All right, so just a quick question then. So if you want to dedicate 4 bits per sample, so every time you record, you're going to record a 4-bit number, then how many different notes could you distinguish between, or how many different notes do you have to choose from when you're doing your recording? Well, just like always, it's 2 to the n, right? So 2 to the 4 is 16, which is not a lot, but again, it's better than the example I mentioned earlier with just 3 bits. So you'd be able to distinguish at every recording between 16 different tones, and each tone that you actually record would have to just be sort of rounded into one of those 16 groups. All right, so let's pull all the pieces together then. So if we're going to use 4 bits per sample, that's the amplitude. That gives us 16 different notes we can pick from. And let's say we are going to choose a frequency of 6 samples per second. Then how much memory do you need for a 5-minute song? So do this any way you want, but 5 minutes is, of course, 300 seconds. And I'm going to do 6 samplings, or 6 recordings, every second. So if I multiply by 6, that says I would do 1,800 recordings, or 1,800 samples. And here I'm going to use 4 bits. Every time I make a recording, I'm going to record a 4-bit number. So I'm going to use 4 bits every time I take a sample. So if I multiply by 4, that gives me my final answer, which is 72,000 bits, which is 9,000 bytes, or 9 kilobytes, I think. Which is, not nothing, but it's not that much. That's like the size of a Word document or something. So obviously, you know that most audio files you have, especially one that would be 5 minutes long, if it was the same amount of memory as a Word document, it's going to sound terrible. And this indeed will sound terrible in all likelihood, because there's only 16 different notes. That's it. 16 different pitches, right? Right? I mean, what am I going to be able to capture with 16 different things? Not a whole heck of a lot. But anyway, just to use some small numbers so that they aren't so super crazy, that's how the pieces all come together. All right, so I tried to draw for you here a little picture, and I'll kind of walk you through. Sometimes it's a little hard to maybe totally sort out the difference between frequency and amplitude and all that stuff. So let's say on the left here, what you see in red here, don't forget about the dots for a minute. But what you see in red here is sound, right? It's a sound wave that's gone over maybe 1 second of time, okay? Now again, if in a perfect world, we would hear all of this, or we would record all of this. If I'm a human listening to someone do this for real, I do hear all of this. I hear all the intricacy. I hear the subtle difference between here and here. I get it all. But when I go to record it, I have to say, all right, well, I got to do the best I can, right? So I chop this up into frequency, right, into frequency pieces, and I record. So what actually is happening when I do that, or what actually, what should I sort of envision? Well, let's take the example where maybe the frequency is very low. So let's say it's actually just 4 samples per second, right? I just made all this up, right? But the frequency is 4 samples per second, which means in this 1 second interval, I'm only going to record 4 times. I'm going to record what I hear, or what the microphone hears, just 4 times. So that's what I did here with the dots here. I'm not sure why I did them in different colors, but right. So when I first start, and this is only 1 second of time, but when I start that second, I record what I hear. And then about a quarter of a second later, I record again. And a quarter of a second later, I record again. And a quarter of a second again, I record one last time, and that's it. So what is it that I actually get is I'm only going to get 4, and even if I have high amplitude, let's say I have a very fine, I can recognize maybe 10,000 different sounds. So I'm ready. I can distinguish between a lot of different sounds. But if your frequency is low, then all you're ever getting, in this example anyway, right, is that for a second of sound, of real life sound, I'm only getting 4 recordings. So what does that sort of do to the graph, I guess, of my sound wave? Is that it flattens it, or I don't know what you want to call this, sort of turns it into little steps, I guess, as opposed to a nice flowy curve like this. And what is it? What's the sort of playback going to then be when I record with a low frequency? Is that it's going to take this note, whatever it is, whatever this sound is, and it's going to play. Here it is, right? And it's going to play it for a quarter of a second. And then the next recording happened here. So it switched. It's a different sound. It's a different tone. So then it's going to say, all right, then switch to that tone for a quarter of a second. And then it made another recording, so switch to that tone. And then lastly, switch to that tone for a quarter of a second. And that's it. So I play this back, and I get a note. I get a sort of note here. I get a note a little higher. I get a note lower, and then a note really low. But that's all I get. I just get little beeps, I guess, of this followed by this, followed by this, followed by this. And that's all I get for what was probably quite intricate sound. Okay, so that's sort of the pitfall, or that's a way of imagining or seeing frequency and what role that has. And of course, it's easier to talk about bad frequency or low frequency because it helps you depict why, if I look at this and hopefully understand what I just said, this is not an accurate representation of this, which is supposed to be quite, orchestral almost. Okay, so frequency, that's the sort of downside, I guess, or that's what you can envision frequency does for you. Now, on the flip side, how about amplitude? What if your amplitude is bad or is too low, but your frequency is good? So now the difference between this picture and the last one is that rather than saying, flashback for just a second here, I said, all right, we have very good amplitude, meaning I could distinguish between this note and probably this note and this note and this note and this note and this note. I could distinguish between all those different ones. My frequency was crappy, and so I only ever listened and recorded here, 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 and here, right? So my problem wasn't that I couldn't distinguish between a richer palette of sounds. I just didn't have a lot of opportunities to do so. Now for amplitude, if your amplitude is low, but let's again say maybe the frequency is high, now I have the other problem. So the frequency is high, which means I'm doing lots of recordings. I'm recording here and here and here and here and here and here again and again and again and again and again and again. Maybe I'm recording 1,000,000 times in this 1 second of real life audio, which means as soon as this tone changes, I'm going to get it, right? Because if I'm recording and recording and recording and recording and recording all these times, then I'd be able to know, oh, okay, I got a recording for here and a recording for here and a recording, right? I'm gonna get them all, which sounds good, and it kind of sounds like we fixed our problem from the last slide. However, if your amplitude is too low, remember amplitude says how much memory are you going to use every time you make your recording. Well, let's use the same number and say I'm going to use 2 bits, which of course means I get only 4 distinguishable tones or notes. So if my amplitude is low, 2 bits, then I only have 4 codes, which these should look familiar, right? That's 0, 1, 2, 3 in binary, right? Then when I'm recording, even if I'm recording here and here and here and here and here and 1,000,000 times in here, every time I make a recording, I'm only allowed to use these 4 codes, which means basically I'm going to only have 4 different sounds in the playback. So the problem, right, is that even though I'm recording and recording and recording and recording, this entire time period, while I might have 25,000 or 250,000 recordings, they're all the note 1-1, right? Or in our world, that's a 3. So it's just tone 3 this entire time. And then when I get to here, yes, it's true, since I'm recording and recording and recording, I notice as soon as I switch, however, with my crappy amplitude, I say, oh, okay, it's not code 3 anymore. it's now code 2, right? 10 is 2. So I record 2 or 10 So that whole time period is all the same note. Okay, and similarly for this time period and then for my last little time period. Okay? So the problem is that then how does this play back? It just plays back as a high tone for a quarter of a second, somewhat lower tone for a quarter of a second, lower, and then very low for a quarter of a second each, or so. So not great, right? Because while I recorded very frequently, what I was recording each time was not very robust. I didn't have a lot of options of notes to pick from, and so consequently, I wasn't able to tell the difference between the recording right here and the recording right here, even though in human world, we would say, oh my gosh, that note there is way higher than that note there. In my recording, they all got recorded as 1-1. Okay? So this is an exaggeration, of course, right? But this shows you the picture of why what happens when one is sort of out of whack. So obviously the answer is you need a lot of both in order to make this really work. So this is what's called waveform audio, which is the sort of modern representation format for stereo quality sound. So used in CDs, used in digital music as well. What's the standard, right? Or what's where do you want to be in order to avoid being this guy or this guy, right? Both of these playbacks. Oh, I should have said the recording you get. This was the same audio for each picture. But the recording you get is different, actually, right? This recording is here, 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 and this one is here, 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 right? So it's a different. It's a slightly different picture. They're both terrible, and neither one of them is exactly this song, right, or this audio that we're supposed to be seeing here, which obviously goes up and down and up and down and up and down a lot. So how do I get closer to these pictures? Well, obviously then I can't have either of these be low. I need high frequency and high amplitude. So how high is high, I guess is a good question. So for stereo quality sound, you have to jack the frequency up, and a standard recording records 44,100 times every second. I mean, it's kind of amazing to try to wrap your head around that. A second is not a long period of time, but audio that's recorded, that I'm recording now, in fact, 44,000 recordings, or binary numbers are stored every second in order to capture all of in order to capture changes, right? To try to say, okay, at the beginning of that second your voice was in one spot, and at the end of the second it had changed, gone up and down a few times maybe, and tones changed and things like that. 44,000 times per second is how often the sort of high quality, right, music is recorded. So kind of amazing, I guess. How about amplitude? Well, so I need a decent number of pitches or tones that I can record and recognize. So what's decent? How much do we need? This isn't as insane as a number, perhaps, but 16 bits is the standard, which is 2 bytes, right? A byte is 8 bits. So it's 2 bytes or 16 bits per sample is the standard amplitude. And how many notes or tones does that give us? 2 to the 16, right? We know that's our formula. So for 16 bits, I get 2 to the 16, which is about 65,000 different possible tones that can be recorded. And since I'm doing them very frequently, obviously, right, 44,000 times a second, you can pretty accurately represent music and sound, right? You can piece those things together. You're getting 65,000 choices for what to record 44,000 times every second, right? So that's a lot of options in a very short window. And that is how we can represent the complexity of the real world and sound in the real world. Okay, so how much memory does that translate to? So if we use the waveform standard, then if you're doing 44,100 samples per second, and you're taking 16 bits per sample, let's say you have a 200-second long song, then you're going to record 141 million bits to get stereo quality, or sort of modern quality, of a 3 minute and 20-second song. And that's about right. I mean, this isn't necessarily 100% set in stone, but this is approximately right, that if you convert this into more modern lingo, this is maybe about 10 megabytes, 10 to 20 megabytes, which is fairly standard for an audio file, a rich music file, like an MP3 or some other format, would be about that much memory in order to store just 3 minutes and 20 seconds of music. Okay? Right. So the last thing to add, at least in terms of material, is that, of course, in reality, we know that most music has more than one, what we usually would call, channel of sound. And so, again, since our ears are so amazing, we can layer the sound through different channels and lay them on top of each other so that when we play it back, we hear multiple channels of sound simultaneously, and our brain is able to handle that, of taking vocals on top of music and putting them together and saying, oh, okay, yeah, like the person is singing to that song. But when they're recorded, you probably know this, they're recorded separately, usually, not always, right? If it's a live recording, you might get that the audio that they've tried to capture it simultaneously. But generally, right, you might have different audio streams, or the word we'll use is channels of audio. So examples of this might be that you have, for someone playing the piano, you sort of have two parts, the bass part and the treble part, or the right hand and left hand. So maybe you would record those two channels separately so that the playback would be on top of each other, but that would more accurately represent what you hear instead of recording it all at once. In bands, of course, there's many tracks, many channels, probably one for each component of music that you might have. So maybe if you have vocals, a guitar, a bass, and drums, you'd record these all separately and then put them on top of each other when you actually make the recording. But of course, if I'm going to do this, which I will do to improve quality, this again, of course, means way more memory, because then I'm not so much saying, okay, I'm going to do one channel, which is to record however many bits. I'm going to need to do this however for every single channel, and if they're all the same amplitude and frequency, and I'm doing 4 channels, it maybe is 4 times the amount of memory. So this is where it really starts to add up, and we really start to get into some pretty large numbers to have good quality audio. So why use this, right? So we've all maybe experienced this, but imagine you're sitting in a room with 5 people giving speeches at the same time, which is probably a terrible situation. But if you're trying to record, right, and by that I mean, sort of be a reporter, I guess, on what's happening, well, I mean, I don't know what you do, right? What do you even write down if your task is to make a summary of these speeches, but they're happening simultaneously, right? You can't really listen to all 5 of them at the same time. You don't have like 5 hands either to be able to be sort of note-taking. Even if we did, I think our brain wouldn't be able to handle trying to separate them. So I don't know. You'd sort of mash it all together. You'd sort of hear a little bit from one person and write that down for a little bit, and then maybe you'd switch over to someone else, I guess, or I don't know. But you for sure wouldn't get, or you'd just get nothing, right? You'd just sort of be too confused to be able to even sort it out. Right. So of course, right, this is why we need to do channeling, right, which is also, of course, known as sound mixing, to be able to blend these things together to make a nice summary, right? So it'd be much better if you could say, okay, I'm going to record each of your 5 speeches separately, And then I might not play them back 100%, one right after another, but I could maybe blend them together and make a nice summary of what the five people said in general. And, in terms of music, if we think about, maybe we've all done this. I know you've all seen YouTube clips that if somebody, is at a concert and, you hold up your cell phone to make a recording, which granted, we've gotten way better, right? At recorders on cell phones are so much better than they used to be, but they're still not fantastic, right? What happens? You get this sort of, and it's almost an indescribable um, thing, but I think you all know what I mean. That if someone's recording, with their phone, okay, first of all, they're in the audience, so they're not sort of right near the music. But when you're there and you're at a concert, maybe especially not a super huge venue, you feel like the sound is fantastic, and yet you held up your cell phone and recorded, and you play that back, and you're like, oh, this isn't great, right? But why is that true? Well, if you have a single channel device, which that's what your phone or any recording device, it's hearing everything and it's trying to digitize or trying to record that. So it has trouble because it doesn't know what sounds it's supposed to record. If there's someone behind you talking, you can maybe block that person out and just listen to the music, and you say, oh, I didn't even notice that. But your phone or any recording device doesn't have that ability. It doesn't have a brain. It can't just screen something out. So it's going to have trouble deciding what sound to record, and you sort of get also white noise, right? You sort of have this ambient noise that, again, is probably people just chit-chattering, not even a person right behind you, but just, there's ambient noise happening that it's amazing, but we don't hear that as humans unless you really try to hear it. You just sort of block it out. Well, in a recording, you get all of that. But what happens if you go later and buy a CD that was recorded at that very concert? Well, what's happening? Their instruments are plugged in. The microphone is plugged in, and there's a recording device in the microphones. So it's actually doing channeling when it records the audio, the vocals, the guitar, the drums, everybody. They're all on their own tracks. And, obviously geographically, they try to put those recording devices as close to the sound, the source of the sound, as possible so that there's not a lot of background. And so if you buy a CD or you download music from that very concert, it sounds great. You can maybe tell it's live, but it sounds much, much, much better than your cell phone video that you shot because of channeling, because being able to isolate one instrument or one sound producer at a time and then blend them all together through mixing. Okay, so a quick example of this. So suppose you have a band with two singers and one guitar, and you're going to record, each of them is recording on separate channels, so they're each going to record their own version or their own part of the song. And you guys have seen footage of recording studios, right? Usually, I think the instrumental is probably done first, and then when the singer is putting down their track, they're listening to the music, obviously, so they have it synced correctly. Right, but they don't have the band behind them playing while they're singing into the microphone, right? They're doing this all separately. Okay, anyway, so let's say everybody's going to use a frequency of 100 samples per second. Now, singers probably need a much higher range because the human voice has, again, in theory, infinity number of tones that we can produce. But let's say there's at least 100 different tones that they want to capture from the singers, whereas the guitar doesn't have as many different sounds, so maybe there's 30 variations of sounds from different chords that they want to be able to record, and it's a 4-minute song. So the question is, how much memory is this entire recording going to take? Well, so let's see. So for the singers, it said we wanted to be able to recognize 100 different tones or 100 different notes. So remember, it's 2 to the n is how many notes. So I'm looking for 2 to the n, an n that makes that bigger than 100, or at least 100. So if you just, do the usual trick, which is to just sort of keep doubling until you get over 100, you'll find that 2 to the 6th is 64, but 2 to the 7th is 128. So that's the first time we go over 100. So we need 7 bits for our amplitude. Okay? So the song is 240 seconds long. It's 4 minutes. So it's 240 seconds. We're going to do a frequency of 100 samples per second. And we just said I need 7 bits per sample. Means that for a singer, they're going to record 168,000 bits. And since there's 2 singers, I got to double it. So I have 336,000 bits for just the vocals. For the guitars, it's a similar story, except the only difference is that there's only 30 different tones that I need to be able to distinguish. So we can get by with just 5 bits, right? So again, same game. When does this become more than 30? When n equals 5, you get 32. So you're just over 30. So 5, you need 5 bits per sample. And so it's the same calculation, but just with 5 instead of 7. And there's only 1 guitar, so I don't double it for the fact that there were 2 singers. And I get 120,000 bits. So if I put these tracks on top of each other, which we're not going to talk about how to do that, but if I did, right, I would just need, I need all the bits from this group plus all the bits from that group. So if I just add them up, you get almost 500,000 bits, which again is not a lot, right? So this is not a realistic example because remember, 100 samples per second is way below the waveform. Waveform was 44,000 samples per second, and n equals 7 bits. Remember, it's 16 bits is sort of real stereo quality sound. So these again are lowballing it, but just so at least the numbers are a little more manageable. We'd end up with just under 500,000 bits. So I wanted to finish with at least just a little bit of an explanation of sort of the physical world of speakers and microphones or recording devices, right? So this is mostly, computing how much memory and all these usual tricks. Sure, we want to be able to do that. But just physically, practically, how does sound translate between digital, meaning memory, and our world, our ears or our voice? Well, how does a speaker or microphone work? So what you have pictured here is a sort of diagram of a microphone or a recording device, if you don't want to say microphone. What happens? So in the real world, sound is traveling in waves. So there should maybe be a person here with person's head maybe at this end of the spectrum. And if someone is speaking or singing, sound is coming out of their mouths in waves. I know it's kind of weird to imagine, but that's true. That is actually what's happening. That when you speak, sound waves are coming out of your mouth. So they're bouncing around through the air at an amazingly fast speed. So we can't really see it sort of flow, but there they are. Okay, so this is the real world. This is the intricate details of sound in the real world. So if I'm using a microphone or a recording device, what happens? Well, the sound in the real world here is actually funneled. I know that this doesn't. This sounds like a sort of looks like a science project or something here from middle school, but this really is actually what happens. That the sound is gathered in some sort of a focusing device. In my picture, it's a cone. And how does that translate into zeros and ones, right? I mean, if we believe the story that I've been telling you for the last hour, somehow sound translates into binary. Okay, well, we know the system for the binary recording, but we don't know how physically does that happen. How does it know that it's a this note way up here versus a this note way down here? Well, so the sound is gathered and focused because sound waves are actually very, very. The amplitude of a sound wave is way too high to try to manage. So it's focused. It's gathered and focused in a smaller sort of end of this device. And there's coils here that are attached to this focusing device that vibrate. The vibrations are then sort of extracted into with a magnet, with an electromagnet, and separated into zeros and ones. So as crazy as it sounds, when this sound is coming in, the note of is it this note versus this note produces slightly different vibrations in the coil, and those are all translated. And then what you see at the end here is red and black wires, which corresponds to 0 and 1. So I think black is usually 1, and so red is 0. And we would see different vibration, literally actually electricity, voltage, would ping. And it would say, okay, as I'm recording, I'm taking these things, the vibration is generating differences that I'm noting with these wires that are recording zeros and ones. And that's, of course, then connected to the memory. So it's sort of like an old school, what was it? Like a telegraph, right? Telegraphs actually like vibrated. That when it was trying to, I know this would only be in a movie that you would ever maybe see this, but sound is not human sound is coming through, but vibrational sound is coming through, and people would sort of tap to be able to read what the message was. And it was the vibrations were generating different codes. Same idea with this. So real life audio out here, right? Focused, I don't know what the right word would be, gathered, differentiated with vibration, and the binary code zeros and ones popping out and stored in memory. That's how a microphone works from left to right. Notice, actually, this should look a little familiar because our ears are the human version of this paper cone. Why do we have ears? It's a good question, I guess. But the answer is to do exactly this. Our ears, right, are a somewhat fancier version, I think, of a paper cone. But they do the same thing, right? Our ears are big on the sort of outside. And what do? Believe it or not, they do focus sound waves so that our eardrum, which sort of is this region, can differentiate the sounds, right? And then memory is our brain, right? We don't need to record zeros and ones. We record, okay, well, I recognize that sound. But that's what our ears look like, right? So, I mean, this is an awful thing to think about, but, if you chopped off your ear, you could still hear, but you wouldn't get that sound focused, right? And if you've ever sort of exploited that, even just by making your ear bigger, if you sort of cup your hands and put them behind your ears, which I'm doing right now, I know you guys can't see that, the sound changes, right? And in fact, it's sort of less filtered. You can hear better in some sense, right? That's why people put a hand to their ear when they can't hear somebody. You can hear better, but it's not as filtered and processed because you've sort of messed with the system. Same idea though with a microphone. Being able to record, and a better microphone is going to be better, and it's going to have a more, not necessarily larger cone, but a more sophisticated cone to try to focus out the outside noise and just hear and record what the actual audio is. Okay, and a speaker works the opposite way. So this is also a picture of a speaker if you read it from right to left. What happens with a speaker, so let's say your headphones, for example, or a physical speaker, is that it has zeros and ones that it's going to try to play back. And so what happens? Zeros and ones are fed into a computer, basically, or a mini processor instead of a magnet. This is then sent out in low vibrations to a cone. So believe it or not, I mean, I know you can't really see it too well in your headphones, but if you think about speakers, maybe in, again, older speakers, you could actually see it much better. There is a cone inside the speaker that is doing exactly this. It's taking the vibrations that are corresponding to different notes, and it's amplifying it would be the word. It's making it bigger so that when it gets out to human world, it's in this right sequence, and we hear it just as we would if we were live and in person. Okay? So it's kind of amazing, right? I don't know. I mean, images, coming up with a system for storing images is pretty neat, but it's still a visual, physical thing. Sound is not visual or physical, right? It's in the air. So being able to come up with the ways, mechanical ways to kind of understand it, it's pretty neat, I think. So, um, oh, I said this already, right? But so a good recording device or a good speaker has sophisticated tools sort of in this region right here to produce both high frequency and high amplitude, whereas a poor one is lacking in one, or maybe both. So, what else is there to do for you guys? So similar to last week, I posted some problems with this video in Canvas in the module on sound that are just a couple of other maybe practice problems for you to try. I did some problems in this video, so you probably don't have quite as much to hopefully look at, but try them. Those again are just for practice. So check them out. It's sort of a series of questions. And there'll be solutions posted to those as well on Canvas. So check those out, try them, and then when you're done with all of that, try the actual homework, which of course, as usual, is a Canvas quiz that you can take and try. I think there's about 10 questions or so in that one, so it's a little bit shorter. This is a little bit of a shorter unit anyway. So try those. Try those questions as usual. And this is sort of the last video in this kind of series, I guess. So our next videos will be talking a little more about sort of the hardware and how the physical electricity and transmission and flow of things happens in a computer.